So the topic for today is cryptography and complexity, a topic that many of you had expressed interest in learning about. So today, as I said, is more of an introduction. It's more on definitions, maybe less on proofs, though I will try to prove a few things for you. And so the setting, the usual setting is we have two people, Alice and Bob, who wish to communicate with each other. And there is an eavesdropper, Eve, who is hearing the conversations. So we'll assume that Alice and Bob have access to a private key of length n. So this is a private key. And typically this private key is generated uniformly at random. So I will just put an in R, which just means that it is a uniform random string. Now what Alice wants to do, so we'll just consider the setting of Alice wants to send a message to Bob. So X is some message, 0, 1 to the M. And this is what Alice wants to send. And typically, it's useful for us to think about even this message being distributed at random. Although maybe this message comes from a distribution, what Alice can do is, maybe just to fool Bob or just to make this look random, can pad it with some extra random bits so that the message looks like it's random. And she would then send this message to Bob. And what Alice will send is an encryption. So it's an encryption of X. But this encryption, of course, depends on the key K. So that's what Alice sends. Eve can read this message. So Eve knows Y. And then what Bob is going to do is Bob is going to reconstruct X by decrypting Y. All right, so this is the message X. There is a key K. Y is what is transmitted. Right? So Y is the encryption of X, and then X is the decryption of Y. Okay, so this is the basic setting that we have. And so first, just a couple of basics on what we require from these functions. So decryption works, which simply means that for all pairs K and X, the decryption of K of the encryption on X must be equal to X. Right? What this means is, let's just say that suppose the string lengths were known to everyone. So let's just say Eve knows Y, maybe Eve also knows N and M. So, and Bob also knows these things. So what this means is that for all X prime of a fixed length, and for all keys, the encryption of X should not be equal to the encryption of X prime, right? Because the decryption has to uniquely get X from the encryption. And so if two different strings encrypted to the same string, then obviously decryption cannot work. And this is going to be, it's a very simple fact, but it's going to be crucial on the analysis that we do, that essentially the encryption function is a one-to-one function. Okay? Does that make sense? So for all keys, the encryption function is a one-to-one function. Okay. So now let us define what perfect secrecy is.
Sorry,
Yes.
Sesh. So you're only considering non-randomized encryption?
Sorry, say that again.
So are you only considering non-randomized encryption?
What do you mean by non-randomized encryption?
So if I understand correctly, you said encryption is one-to-one, but you can get different ciphertext for the same message if you add some random nonce or some random.
So this is saying
again or something, right?
If you fix the key,
yeah,
then So the only shared secret between Alice and Bob is the key.
Yeah, but then again, you can sample something else that at random and use that, and also send that.
But then Bob would need
initialization vector, commonly called.
You mean they can sample an initialization vector and then, but then how would that be transmitted? Would that also be encrypted or be sent in plain text?
It can, or it can be sent. It can be sent in plain text. It can be sent using a PRP of some sort.
In this stage, if it was sent as part of the plain text, then it would essentially be that Bob could. So the point is that there is some portion of the message that basically has to be unique. Whatever depends on X has to be unique. Everything else. So we could either assume there is some common knowledge between everyone, which you could call some K prime. And then for all K and K prime, this has to hold. Mm-hmm. Right? Because in your initialization text,
that makes sense. Exactly. But your definition sort of skipped that.
Well, yeah, my definition skips that because in some sense, I could fold that into the encryption.
Okay.
And the decryption, right? So I can assume that is fixed unless.
I just wanted to be
sure
that we're on the talking about.
Yeah, so you could introduce that, but I think that it would only introduce more notation without explicitly, changing anything here.
Okay. Yeah. Okay. Thank you.
Yeah. So let's define what perfect secrecy is. So perfect secrecy is, so you have these pairs of functions E and D is an encryption scheme, right? So this is just a pair of functions that satisfies all of these conditions. So ED is perfectly secret if so this is a very, very strong condition. It says that for all X and X prime in 0, 1 to the M, and for all keys K, the distribution of the encryption of X and the encryption of X prime are identical. Where again, recall that K is chosen at random from all possible strings. So this is what perfect secrecy means. It means that you choose a key at random, then choose any two messages. The distribution of these encryptions of these messages are identical. Does that make sense? So these distributions are identical. The distribution is over the randomness of K. So one way that I just like to imagine this is, think of a map between plain text, and this is X, and this is the ciphertext, which is Y. So if you look at any X and X prime, this is mapped to various different ciphertexts depending on the key. So for key K1, you get this. For key K2, you get this. K3, you get this, so on and so forth. Similarly, for X prime, you get some set of messages. These distributions are identical, meaning that if you simply see the ciphertext without knowledge of the key, it could have come from any plain text, right? So conditioned on seeing the ciphertext without knowledge of the key, the message is equally likely to be any plain text. Does this definition make sense? Any questions about this? So this is perfect secrecy, because this means that on seeing the message, on seeing the ciphertext, on seeing the encryption, it is impossible to distinguish any plain text from the other. Now, a simple encryption scheme that guarantees perfect secrecy is a one-time pad. And I guess formally this goes back to Shannon. So here, the key and the message will be of the same size. The encryption of X is quite simple. It's just a bitwise XOR. So this is a bitwise XOR. And the decryption is also a bitwise XOR. This achieves perfect secrecy. So this you can verify. Essentially, if you randomly flip each bit, then you're equally likely to generate any ciphertext from a given plaintext, but can be used only once. It can be used only once. Why? Because if I encrypt a message X and I encrypt a message X prime, suppose the eavesdropper, Eve, could see both of these. If she were to simply XOR these with each other, she would learn the XOR of the messages X and X prime, so learn something. Which kind of makes sense because in a one-time pad, the message and the key have to have the same sizes. But here, you can think of the messages X and X prime. So there are two messages. And so this can be used only once, but it achieves perfect secrecy. Okay, any questions about this? Does this make sense?
How does Eve learning about X or X prime help Eve?
Well, just think of it as Eve has then learned some non-trivial information about the messages.
Okay.
That's all. And so therefore, what this means is that perfect secrecy is lost.
Mm-hmm.
Because the distributions
okay, I see.
are not identical anymore.
Yeah.
So think of it, it's like conditioned on what the ciphertext is the distribution on the plain text still uniform? And in this case, it would not be.
Yeah, it's like if you have like a long message and you use a short seed and you just XOR like every part of the message with the same seed, that's no longer perfectly secret.
Exactly, you are revealing information, right? Yeah. Okay, so let's actually start with a simple, but what I think is a fairly illuminating proof. It's a useful proof to have, is that so a simple claim is that no perfectly secret encryption scheme can have the key length shorter than message length. So what this is saying is that perfect secrecy implies that the key has to be at least the message size. Right, so this is the key length. And this is the message length. And so in a one-time pad, n is equal to m, hence it's optimal. So this very simple scheme that we showed is optimal for perfect encryption. Okay, so let's prove this. The proof is quite simple, but it's illuminating. So why should this be the case? Why should this be the case? That if you actually have a key which is shorter than the message, then you cannot have perfectly secret encryption. And really, it all just boils down to this fact. It all just boils down to this fact. Okay. So let me draw a picture. And hopefully that picture will illuminate the proof. So this is the plain text or the message, right? So this is the plain text or the message, same, which is X, right? And this is in 0, 1 to the M. And here is the ciphertext or the encryption, which is supposed to generate, which represents EKX, although K and X could have different values. Okay, so suppose you fix a value of K, fix a choice of K. Just fix any key. What do you know about this function? So this induces a function, right? Because if you fix an encryption, you get a function. And suppose I were to just draw it as in, okay, so this is the map of X, and this is EKX. If you choose another X prime, what do you know about this? What do you know about the image? Assuming this is just an encryption scheme, any encryption scheme.
They're different?
They're different, right? Exactly. That's what I said here, right? Decryption works, so it just means that if you take two different strings and you encrypt two different strings, you have to get different results. Okay? So how many possible ciphertexts are there if you fix a key? If you fix a key, how many ciphertexts do you have?
You've got to have at least one ciphertext per X, right?
For X, and there are 2 to the MXs, right? So you have 2 to the M of these. Right? So for a fixed key, there are 2 to the M ciphertexts. Okay, now from this, can you infer that the key length has to be at least of length M? Assuming perfect secrecy, what do you know about different keys with respect to the same X? Suppose you have some X prime here, and this is EK of X prime. What does perfect secrecy tell you about this message and this ciphertext?
They were equally likely to be, just like X was equally likely to be mapped to EK of X prime.
Exactly. So X must be equally likely mapped to X prime. Means that if you look at this edge over here, there is some K prime such that X mapped with the key K prime leads to EK of X prime. Does that make sense? So there has to be some chance over the choice of your key that X gets mapped to X prime. And this has to hold for all of these ciphertexts. So what this means is, for every X prime, there exists a key K prime such that the encryption using K prime of X is the same as the encryption of X prime using K. Does this make sense? And this is because of perfect secrecy. Perfect secrecy. So X must have some chance, X must have some chance of mapping to EK of X prime. Right? So for every X prime, there exists a key K prime such that encrypting X using K prime leads to the encryption of X prime using K. So the prime is switched. Okay, now can you complete the proof?
So there has to be 2 to the m keys.
There have to be 2 to the m distinct keys. Exactly.
Well, what if
because
they're not? Oh, because it only maps to one of them.
It only maps to one. So if you choose different key, if you choose the same key K prime, you have to get the same result. This is just saying that treat this part, the left-hand side, as a function that depends on K prime. If you're fixing K and you're looking at K prime, and here you're fixing K and you're looking at X prime. So there exists a key prime such that, and so thus EK prime X, fixed X varying K prime must take on at least 2 to the m values. Hence, there are at least 2 to the m distinct keys. So the key length n has to be greater than or equal to m. Right? So that's the end of the proof. That's the end of the proof. Okay? Does this make sense? So it's just a counting argument. It's just a counting argument that says that perfect secrecy implies that the key has to be greater than the message. The idea is simply to say if you fix a key, so fix a choice of key, look at all the possible ciphertexts. There are at least 2 to the m ciphertexts because there are 2 to the m messages. Now, by the condition of perfect secrecy, if you look at the ciphertext, you shouldn't be able to distinguish where the message came from. So there has to be some choice that every possible ciphertext comes from every possible message. And so if you fix a message and vary the key, you should be able to get all possible ciphertexts, which means there have to be at least as many keys as there are ciphertexts. There are 2 to the m ciphertexts, and hence there are at least 2 to the m keys, and so n is at least m. So the one-time pad, this very simple encryption scheme, is actually optimal. Okay, is this clear?
Yeah.
Okay. Any questions? Okay, so we're done, right? We've defined perfect secrecy, which seems like a reasonable definition. We have a perfectly secret encryption scheme, and we've proven that it's optimal. So we can just go home. We're done, right? There's nothing. What's left? We've already solved all of cryptography here. So what's the catch here? Yeah? Any suggestions? How am I going to make progress beyond this?
Reduce the number of keys.
Sorry?
Reduce the number of keys. Right now it's like exponential.
But there's nothing I can do, right? I just proved to you that no perfectly secret encryption scheme can have a key length shorter. And so I've proven to you that a perfectly secret encryption scheme requires a key length that's at least a message length. And I already have an encryption scheme that achieves that, which is just the XOR. So, okay, this is an important point to ponder, right? Which is when people come up with definitions, when researchers come up with definitions, and then they prove some theorem, maybe a very simple one, how do they go beyond it? So clearly, there seems to be something unsatisfying here. And what is unsatisfying is that the message length and the key length have to be the same. Usually you think of the key being smaller and you're transmitting a large message. And what we just proved is that it is not possible to achieve this. Now, and this is exactly where computational complexity came in to sort of save the picture. Or rather, create the picture and save the day. Nothing about what we said says anything about computational complexity. So now, thinking in terms of computational complexity, can we generalize? How can we proceed in some way using computational complexity? That's my question. And think about Eve. And think about what you're assuming about Eve.
Maybe if Eve has less power, then the key length can become shorter.
Exactly, right? So in perfect secrecy, what you're effectively assuming is that Eve is all powerful. Or at least you're assuming that Eve is like an exponentially powerful machine. Because if Eve can simply look at a message and tell you, Eve, you're assuming here that looking at the ciphertext, Eve knows the entire distribution of the plain text. Right? That's basically what we're assuming. So what we should do is make Eve computationally bounded. This is implicitly assuming that Eve is computationally all-powerful. So what we're now going to do is going to say, suppose Eve is computationally bounded. So let's assume that Eve is computationally bounded. And so a reasonable assumption is that Eve runs in polynomial time. And so I'm going to assume that Eve runs the breaking function B. Right? So I'm just going to, I would call it E, but then E is for encryption. So I'm going to say Eve is running a breaking function. So Eve runs the breaking function on Y and wants to infer something about X. And remember that Y is the encryption of X. Right? So Eve is in between here, and Eve is going to run her breaking function on Y, hoping to discover something about X. Perfect secrecy says Eve should not be able to discover anything about X. Eve should not be able to discover anything about X. Okay, so now this is where computational complexity and cryptography are going to meet in this first lemma over here. Just suppose P is equal to NP. Let the encryption-decryption be any encryption scheme running in polynomial time, which simply means that both the encryption and decryption functions are in polynomial time. Then there exists a polynomial time function B, which is the breaking function, such that for all message lengths, okay, I'm going to write something here and then we'll understand it.
Wait,
Yes.
the encryption scheme running in polytime just means that the E and D functions run in polytime.
Exactly. E and D are.
But it might take exponential time to, like in K, to like make them.
You mean to design the function explicitly?
Yeah.
Yeah, so assume that actually it doesn't matter how long it takes to design the function. Just assume that it exists.
Sure.
You can even assume that it's actually a circuit often. Often this can be defined in terms of a circuit family, which is that for each K, there exists a circuit of polynomial size that computes, these things. Does that make sense? So you can define EK as really like a family of circuits, and so is DK, yeah. All right. So there exists a polynomial time B such that for all lengths M, there exist two messages that B can distinguish. So let me state this informally, and then I'll state it formally. So what perfect secrecy says is that for any pair of messages, they are indistinguishable, or rather the ciphertexts are indistinguishable, right? So when you choose the key at random, uniformly at random, the ciphertexts are indistinguishable. What this says is that suppose P is equal to NP, let this be an encryption, I forgot the most important thing, and N being less than M. So what I say is, if the key is shorter than the message, even by one bit, and P is equal to NP, then for any encryption scheme, there is a polynomial time function that can actually break the secrecy condition. Specifically, let me just state this formally. It means there exist two messages x0 and x1 such that, so if you choose K at random, which you're choosing as before, so you're choosing the key uniformly at random, and you're choosing a message uniformly at random from here. So I'm going to write something and then we can parse this. The breaking function on the encryption of xb. Okay, so this probability is at least 3/4. Okay, so what am I saying here? So think about Alice, and this is Alice, wants to send two messages, x0 and x1. And so here's Bob. And Eve, wearing some kind of a hat. This is Eve. So Alice is going to choose between one of these messages, encrypt it and send it. So she could encrypt x0 or she might encrypt x1. Eve is going to eavesdrop on these. And Eve needs to tell which message it is. If it's perfectly secret, Eve, the best odds that Eve can get is random guessing, which is a half. So perfect secrecy means that the guessing probability is a half. because there is no, so that's what it means to be statistically indistinguishable. She doesn't know which message generated the ciphertext. But here what we're saying is that if P is equal to NP and the key is less than the message, even by 1 bit, then there exist two messages. Actually, there exist more than just two messages, but it's useful to think of it this way, where Eve can actually look at the ciphertext without knowledge of the key. So the key is uniformly at random, but Eve can essentially guess which message with probability better than a half. So she has 3/4 odds of guessing which message Alice was sending. There are going to exist a pair of such messages. Does the statement of the lemma make sense? And remember, when n is equal to m, then we have a polynomial time encryption scheme such that no algorithm, forget a polynomial time, no algorithm can do this distinguishing. But if p is equal to np, then even by having 1 bit less, this can be done. So what this says is, if you hope to get any kind of secrecy condition with respect to polynomial time eavesdroppers, if you want the key length to be even 1 bit less, then p cannot be equal to np. Does this statement make sense? Any questions? Okay, so I'll show you the proof of the statement, but I want to answer, I think what is really important when you're understanding cryptography in any context, but especially in the context of complexity, is to understand what the definitions are, because the definitions have been very carefully chosen so that we can prove interesting facts. Okay, so let's prove this. The proof of this statement is not as obvious.
What if you're okay with Eve sometimes being able to tell as long as she doesn't learn anything about K?
Well, I mean, in some sense, if she doesn't really need to learn anything about K, right? What she really wants are the messages.
Sure, but as if you're only going to send polynomially many messages, and then the probability that you can tell is exponentially small, then maybe you don't care.
The probability, but even in one pair, she's able to get some non-trivial guess as to what the message is. Only
if you actually send x0 or x1.
You mean if the point is, you'll see that okay, so in this proof only that's true, only if it's x0 or x1. So then what you're saying is maybe you want some perfect secrecy condition under some other choice of messages.
Well, I'm saying maybe I don't care if there's a very, very small chance that Eve can tell what I
Yes,
say.
that's true. Good. So usually you can generalize these to say that suppose these messages are themselves coming from a distribution. And this distribution is known to everyone.
Yeah.
Then you can get results over here under those distributions as well.
Okay.
Right? You can. I think the way to look at this is either you now have to start assuming something about the messages themselves, which then becomes problematic, because then it's what do we assume? Then we have to have distributional assumptions on messages. And again, this is just to show you why P versus NP is central to cryptography. Sure. Right? But in general, when we define okay, you'll see that when we go further, I think I'll address some of those concerns. Okay, so let's look at the proof of this fact. Again, so I guess the issue was, well, this is just two messages, but maybe there are very few messages of this form. But what we can see is that you'll see that the proof can be generalized to deal with more messages. All right, so let's start by saying that let n be less than m. Okay, so now I just want to come up with these two messages. So I'm going to start actually in a very simplistic set of messages. So let S, which is the set of strings, be the support of the encryption over. Okay, so I'm going to write something here, and then we'll see. The encryption of 0 to the m, where k is uniformly chosen over all possible keys. So what this is saying is simply, if you go back to our picture, let me fix the string 0 to the m, just the message with all zeros. Let me look at all possible keys. These are all keys. And then look at what the possible ciphertexts are. This is the set that I call the support of that distribution, right? These are all possible encryptions of 0 to the m. So the language, so think of S induces a language. The language S is an NP, right? Because the certificate, right? So for any S, all I have to tell you is, what is the 0 to the m that whose encryption S is. Hence, S is in P. What this means is, given the encryption of an all zeros message, there is a polynomial time algorithm that looks at a message and can say, yep, this came. I'm sorry, let me see if I'm saying this correctly. Sorry, okay, so I said the language S is an NP. So what is a certificate for anything in S? What is a certificate?
The value k.
The value, it's the key, right? The certificate is the key. The certificate is the key. And so S is in P, which means that there is a polynomial time procedure that can tell me that is this string a potential encryption of the all zeros message. Okay? So consider the following procedure B. So B on input Y does the following. Determine if Y is an S. Remember, this is poly time. If so, output 0. Else, output 1. That's it. So this very simple procedure is just going to output if it sees an encryption of the all zeros message, it just output 0, or it's going to output 1. So first, let me tell you what I'm going to do, and then I can show you what. There exists a message x1 such that the probability that B on x1 outputs 1 is at least a half. So it means that there exists a message where the odds of getting a 1, and remember, this is the probability over the choice of the key. I'll prove this claim, but I'll say that, so now let's go back to Alice. And Alice has two messages. One is the all zeros message of a given length, and the other is this message x1. And she sends these. So this is the encryption of 0m, and this is the encryption of x1. And she's sending this to Bob. So now let's look at what Eve does. So Eve is running the breaking function. If Alice chose the all zeros message, B is going to output 0. If Alice chooses this other message x1, then over the choice of the key, B is going to output 1 with probability half. So the probability over K and B in 0, 1, that XB is equal to B is equal to half times the probability over K that X0 is equal to 0 plus the probability over K that X1 is equal to 1. So this probability is just is 1, because we know that that's exactly what happens here. If Alice sends anything which is in the support of 0 to the m, then the breaking function outputs 0. This probability, on the other hand, is at least a half by this claim, which I need to prove. And hence, this probability is at least 3/4. What this means, in effect, is just saying that Alice, the breaking function, can determine these messages with an odds of 3/4. When Alice is, of course, choosing these messages equally, the breaking function is able to guess correctly with probability 3/4 on the average. Does this make sense? Does this calculation make sense? I have to prove this claim, which I will. Right, so there exists this other message. There exists another message where the odds of guessing the message correctly is at least a half. Okay, so let's prove the claim. So we're going to draw this picture again, this bipartite. Basically, this is like a graph. And I'm going to draw an edge x, y labeled with k. X, y labeled with k. This simply means that the encryption using key k of x is equal to y. Right? So this is this graph that I've drawn. So what I know is let me look at the edges that are coming into K. Now, each of these edges has a distinct key. You cannot have two messages that link to the same Y with the same key, right? So by the one-to-one of the encryption, there are at most 2 to the n, this is the number of keys, edges into Y. Right? This is just saying that the degree of Y, this is, I'll just write this up, the degree of Y is at most 2 to the n. Okay, now let's look at the set S over here. Remember, S was the support of the encryptions of 0 to the n. The degree of anything is at most 2 to the n. The size of S is also at most 2 to the n, because you're basically fixing a string and you're looking at all possible encryptions of it. So it's just the number of keys. Hence, the number of edges into S is at most 2 to the n times 2 to the n. So it's at most 2 to the 2n. Okay, does this make sense? Okay. So you have at most 2 to the 2n edges going out of this. Okay, so now let me try to sort of for every x, let d of x be the number of edges from x into s, right? So for every string, I can say how many edges are going into the set S. So I know that the summation over all x over all messages of d of x, that's the total number of edges that are going into S. This is at most 2 to the 2n. So the mean, the average value of d of x is at most 2 to the 2n divided by 2 to the n, just averaging. All right. I hope I'm doing this correctly. Yes, I am. Okay. So the average dx, the average degree of x into s is at most 2 to the 2n divided by 2 to the m. Now we assumed that n is less than m, or in other words, m is at least n plus 1. So I have 2 to the 2n divided by 2 to the n plus 1, which gives me 2 to the n divided by 2. What this means is that, going back to this picture here, remember this is S. The size of S is 2 to the n. But there is a vertex, there is the average degree into it is less than half of that. The average degree is less than half of it. So there is some vertex, there is some x1, so that if you look at all of its edges going out, only half of them are going to be in here. The rest of the edges are going to fall outside this region S. So there exists an x1 such that the degree of x1 is at most 2 to the n divided by 2. Hence, the probability over the choice of the key that the encryption of x1 lies in S is at most a half. So if you go back to this, remember, what happens is if you take the encryption of x1, if the encryption lie in S, the output would be 0. If the encryption lie outside of S, the output would be 1. And what this is saying is that with half probability, the encryption will lie outside of S, and hence it will be 1. So this is equal to the probability over K of the encryption of x1 not being in the set S. And that's exactly what we show. The probability of it being in S is at most half, and so the probability of K of the encryption of x1 being not in S is at least a half. So again, just to pop back up a bit, what's going on here is what we're saying is, quite simply, let's go back to this picture. There is a message, fix a message, and look at all possible encryptions of that message. there must exist some other message x1. So if you look at its image, only half of it intersects, the rest of it lies outside. So if you were to predict 0 for everything in here, then at least with half odds conditioned on x1, you guess that it's x1 correctly. And you're always going to guess x0 correctly. So this is just saying that, and the reason why you have this intersection, this happens because the key is less than the message. So somehow there has to be regions of low overlap. All of these cannot overlap completely because the message length is more than the key size. In the previous example, in perfect secrecy, all of the images are completely overlapping. They're always the same. But because you don't have as many keys, you must have situations where there are two messages that don't overlap, whose ciphertexts don't overlap that much. And when P is equal to NP, then you can exploit the fact that certificates, you can compute certificates efficiently to start distinguishing messages. And again, if you kind of walk through this argument, you can actually show that this will happen with high probability for many pairs. Right? Because this is just a counting argument. This is just like an average degree argument. Indeed, what it shows is that even if you pick an average x1, you can distinguish it from that all zeros message. So if you pick an average x1, you can distinguish it. Again, so the essence of the argument is if you look at what x0 maps to under the keys, and you look at what x1 maps to under the keys, their overlap is small. And so therefore you can distinguish them. So of course you can distinguish them in general with any machine, but here you can, because of the certificate viewpoint, you can distinguish them in polynomial time. And that is the essence of the argument.
And
yes.
Well, I guess for any language that's in NP, you can like compute the certificate in NP, right?
You can compute the certificate in NP, yes.
So why can't Eve just compute K?
Well, because, you don't know. There could be a different choice of K that mapped x1 to the same string.
I'm saying, like we said, the language, there's a language that's in NP and the certificate is K, right?
Well, yes, you can compute the key, but that key would only be correct if Alice was actually encrypting x0.
Oh, I see.
Like Alice may have been encrypting x1, in which case your certificate doesn't really mean much.
Yeah.
But what you have is you have enough statistical evidence. You have sort of statistical evidence that this message is probably coming from x0 or x1. But you never have certainty.
Yeah, that makes sense.
Yeah? Okay, so does this make sense? Any questions? So, and if you walk through this argument, you can actually show that this all zeros and all ones can be represented with sort of any, you can choose pairs at random for this. The essence of this argument, again, is simply saying that when P is equal to NP, if Eve is trying to distinguish between two messages, suppose Eve knows that Alice is going to say, Alice is going to say something like buy or sell or something like that. Then Eve can essentially distinguish between those messages with non-trivial probability, even when the key is just 1 bit shorter. So this is very strong. Even when the key is 1 bit shorter, Alice is able to Eve is able to distinguish. So this leads us to what can happen, what are the assumptions that we need for cryptography? So I'm going to now write out a few definitions. So let me define a function epsilon going from n to 0, 1, or sorry, n to is negligible if epsilon n is n to the minus little omega of 1. What this means is that epsilon n is less than 1 over n to the c for all c. Right? So epsilon n is less than any polynomial. Hence, a bit with bias epsilon n is indistinguishable from a random bit. Uniform random bit. And now let me give the important definition of what is called a one-way function. A polytime computable function f is a one-way function if, well, this is defined with respect to p versus n, with respect to polynomial time or polynomial size circuits. You can do either. If for all polynomial time procedures b, which is the breaking function, there exists a negligible function epsilon. Okay, so this is for all polynomial time procedures, there exists a negligible function such that for all n, if you look at the probability of generating x, which is the message, uniformly at random, I should say for all, okay, so for all m, so for all m, the probability that b, given the one-way function on x, so and f of x is equal to f of x prime. So this is saying, what is the probability that if I gave it a random x, I applied f on it, I gave b access to f of x. So think of this like an encryption, and you just have to invert. You have to find the pre-image. The odds of finding the pre-image is negligible. This is saying that inversion is hard. Inversion is hard. So again, a one-way function is a polynomial time computable function, so that if you give a polynomial time procedure, a breaking procedure, the evaluation of the function and say find a pre-image, finding the pre-image is hard. So the odds of getting one are just negligible. The odds of inversion are negligible. Does this definition make sense? Okay. And so the big conjecture of cryptography is that there exists a one-way function. And indeed, there's an even stronger conjecture. It's believed that multiplication is a one-way function. So you have to phrase it a little carefully what I mean by multiplication, but if you take two prime numbers, P and Q, each n bits long, so your one-way function is simply f of pq is just p times q. And so the inversion problem is given the product PQ, compute P and Q. And so the inversion problem is this, and it is believed that the inversion, and this is simply factorization, and it's believed that this factoring is hard. And hard just means not polynomial time. It is not believed to be NP hard, as we've discussed multiple times. If factoring was NP hard, then NP would be equal to co-NP. But the conjecture is that there exists a one-way function. Now note, you might say, why do you need a probability here? Why can't you argue this for all x? Why does the definition of a one-way function have a probability and not a for all? Any answers to that? There's a reason why you cannot have this definition for all. Yes?
Because you can just have B return something and it'll always be the inverse of something.
Exactly. So yeah, you could basically, B could pre-compute f of x for some set of x's, and just check if the value of f of x, if the value you're giving is one of those. B can pre-compute a bunch of values, and it would at least have some odds of success. So you need some probability, because this cannot hold for all. Indeed, you cannot have this probability be 0, or you cannot have it be exponentially small, because there are exponentially small odds of getting the right answer, which is simply that B pre-computes some set of f of x's and just checks amongst those. That's like saying that in the factorization problem, a factoring procedure could just pre-compute a bunch of factorizations and just check whether those are correct. It could pre-compute a set of primes and just try to factor with those primes, and sometimes it will be lucky. So it is important to define one-way functions with respect to the odds of success for this reason. Again, these are important things when making a definition, that if you made this probability 0, then the definition is meaningless, because one-way functions would not exist. So it's important to have that. Moreover, this epsilon n is something inverse polynomial. If the epsilon n was inverse exponential, then again, it would not be true. Well, I mean, if it's a very small inverse exponential. So here's a claim, which is, again, it's not very hard, but I think is quite illuminating. The existence of a one-way function implies P is not equal to NP. Why?
But isn't this just the contrapositive of what we just showed?
Not entirely. I mean, we were talking about encryption schemes with with key lengths. I claim that the argument here is much simpler.
Oh, okay.
But it's a different. So what's a one-way function? Given an x, Given f of x, you have to guess what x is. And of course, you might get an x prime so that f of x is equal to x prime. Okay. So clearly, do you see something that's an NP or that you could use non-determinism for?
The output of B.
The output. So you want to define B. You want to define B. But what you want to do is you want to guess. So given f of x, you want to invert, right? Given f of x, you want to compute x. So how would you do that? Think of non-determinism.
So you can non-deterministically guess x prime and check if it holds.
Yeah,
Check
exactly.
if
So what you
its
do
f
is you try to guess what x is non-deterministically. So you can write an NP machine that does it, and you know that can be simulated in P, if P was equal to NP. So again, what we'll do is the opposite. We'll say that if P is equal to NP, then one-way functions don't exist. Do not exist. So here's my procedure B. So what B is going to get is on input, which I'll call Y, non-deterministically guess X. Check if f of x equal to y. If so, output x. Right, this is your procedure. Right, so B, this runs in polynomial time. So B is a non-deterministic polytime machine. If P is equal to NP, then B can be simulated in polynomial time. And B succeeds with probability 1 over the input. Right? So f is not a one-way function. So one-way functions, existence of one-way functions imply that P is not equal to NP. And indeed, this conjecture that there exists a one-way function is the central conjecture of cryptography, which is stronger than P is not equal to NP. One of the big open questions is whether you can build cryptography simply assuming P is not equal to NP, but it is not known how to do that.
There also might be like one-way functions that can't be computed in polynomial time.
Yes, sure. I mean, you can always look at the halting problem, but you could even look at a problem that's exp complete, and we know that that's not in P. So you can probably construct some languages which are exp complete, which means they can run in exponential time and they will not be computable in P. So you need the polynomial time computation. I mean, you can always define one-way function with respect to a class. In general, this is, instead of polynomial time function, I mean, this can also be defined in terms of circuits, circuit classes. So you look at all polynomial size circuits, and then often they will parameterize one-way functions with respect to circuit classes, or with respect to the power of the procedure. So now that we have this notion of a one-way function, I want to go back to our definition of perfect secrecy and now weaken this definition with respect to polynomial power eavesdroppers or breaking functions, and then show you, write out the theorem of what is possible for encryption schemes, non-trivial encryption schemes, where the message length is larger than the key size. So let me first define a computationally secure encryption. So what we had was perfect secrecy, and now I'm going to define a weaker notion called computationally secure. So again, ED is an encryption scheme. Encryption scheme that runs in polynomial time. Right, so what we'll say is that the scheme is computationally secure if for all polynomial time breaking procedures B, the probability over, again, the key is chosen at random, the message is also chosen at random, the probability of the breaking function, just that, okay, so I'll write this for all and for all I less than m, the probability that the breaking function, given the encryption, can guess the ith bit. These odds are no better than random guessing. Okay, so what this says is an encryption scheme is computationally secure if no polynomial time procedure can guess the ith bit of the message looking at the encryption. Right? This is the ith bit of the message. This is the ith bit of the message. This is, of course, the encryption. What I've defined here is a computationally secure encryption scheme. Right? This is an encryption scheme where, unlike perfect secrecy, in perfect secrecy, the distributions of the encryptions are identical. So no procedure, this is the strongest possible notion because no procedure can look at the ciphertext and guess the distribution better than random. Here we relax it. The breaking procedure is a polynomial time procedure. And essentially what we're saying is for any one bit, any one position, it cannot guess the bit better than random guessing. And one of the main theorems is, suppose one-way functions exist, then for all constants, there exists a computationally secure encryption scheme where the message length m is equal to n to the c. So that means the message is polynomially larger than the key. Right, so a one-time pad, the message length has to be equal to the key size, and if one-way functions exist, you can actually send much larger messages with the same key size. So when the key size is n, you can send messages which are n to the c, which are polynomially larger than the key. This is one of the main theorems that one can prove in theoretical cryptography, assuming one-way functions. This is showing the power of one-way functions. This is still, this is not public key encryption. This is weaker than that. This is weaker than public key encryption. It's basically about sending messages between two trusted parties. But what it says is, if you relax the notion of perfect secrecy to computational secrecy, so as computational security, then assuming one-way functions, you can actually get non-trivial message lengths. Whereas the one-time pad will only give you a c equals 1. Here you can get polynomially larger. Okay, does this make sense? Any questions about this definition? All right. Naturally, I'm not going to prove this in the next 5 minutes or so. But what I can tell you is I can just give you an approach. Well, even the approach, I can tell you what a pseudo-random generator is, because a pseudo-random generator is the key tool used to prove this theorem. And with pseudo-random generators and one-way functions, one can do an entire proof of this theorem. The proof is quite interesting, but it's definitely something I could, let's say, be taught within a lecture. So I'm just going to write what a pseudo-random generator is. A pseudo-random generator, also called a PRG. And so PRGs are the approach to proving the above theorem, or I should say it's a approach. So what's the idea? The idea is, let's go back to the one-time pad. So here's Alice, and here's Bob, here's Eve. So Alice has this message X. Now remember that in the one-time pad, she had a key. And the key had the same size as the message, and Alice could simply send the XOR. In a pseudo-random generator, what we're going to do is, suppose actually the key is much smaller. So this is the actual key, right? So the shared key is much smaller. So this is of size M, and of course the message here is much larger, it's M to the C. A pseudo-random generator basically generates this key K star. It generates a string K star. So K star is a pseudo-random string of longer length. Except K star looks random to any polynomial time machine. Including the eavesdropper. So this string K star is essentially like a random string for the eavesdropper, and hence Alice can use the pseudo-random string for the one-time pad. And that's the approach. So I'll define what a pseudo-random generator is. But think of what happens is you take a small, truly random string and kind of inflate it to a much larger string that looks random. So clearly something, silly like just, copying, taking multiple copies is not going to be a pseudo-random generator. The string K star has to look random enough for any polynomial time machine. And then we can use a one-time pad to achieve our security. And so now I'm defining what a pseudo-random generator is. So let G be a polynomial time computable function, and let the length be some function. So we'll say G is a secure PRG of stretch ln. So the pseudorandom generator is going to stretch the randomness to that length if for all x, the length of g of x is basically this length, is L of x, and for all probabilistic polynomial time breaking procedures B, there exists a negligible function epsilon n such that, so let's say the absolute value of the probability, so x is being generated at random of size of size L of n. This is B of x. The probability that, so let me write this down and then I'll parse it. Minus the probability B of g of x is equal to 1, where now x is actually generated at random just of length n. This difference is essentially epsilon. What this means is, for this breaking procedure, if you feed it a truly random string, that's this. This is truly random. And this is pseudo-random. So if you feed it a random string of length ln, and you feed it a string of length ln, which is generated from the pseudo-random generator, B is unable to distinguish them. So that's saying that here is your breaking procedure B. So the first is you give it a truly random string of length ln. This is fully random. And in the other situation, what you do is you actually take a small random string, you inflate it using the pseudo-random generator, and you feed this to B. B is unable to distinguish between these cases. It doesn't know whether the input was truly random or the input was pseudo-random, with some negligible probability. Then G is a secure pseudo-random generator. So if you have a secure pseudo-random generator, then what you can do is you can essentially apply this procedure. You can apply this procedure that basically takes your initial small random seed, inflates it, and then uses that as a one-time pad. And indeed, the theorem that one can prove is that if one-way functions exist, then for all C and N, there exists a secure pseudo-random generator of stretch ln being n to the c. So this is sort of the main theorem that you need. This is like the main workhorse theorem you need to prove. You show the existence of pseudo-random generators, and when you have pseudo-random generators, you can essentially prove the theorem that there is computationally secure encryption when the message is polynomially larger. Okay, so let me end here and take any questions that you have. This is sort of a high-level description of cryptography. The main thing I hope that you can take away is this notion of perfect secrecy. And I think like going over just that first theorem, that no perfectly secure encryption scheme can have a key length shorter. This understanding that proof will give you some perspective on what is happening. And then the notion that if m is less than n, then you have a polynomial time, and p is equal to np, then you have a polynomial time procedure that can break perfect secrecy. So just understanding those things, I think, will give you some perspective on cryptography and complexity. So let me end here and take any questions that you have.